Hi, today we're going to be solving quadratics by finding square roots. So this is a different way in which we can solve quadratics for quadratics are special cases, if you will. Before we do that though, we need to understand how square roots work and how to use them. We'll start off with a couple properties that we'll be using a lot with square roots. The product property, which simply is if you have the square root of a times b, that's equal to the square root of a times the square root of b. Those are synonymous with each other. So in other words, we use this property to help us simplify radicals, and all our answers we present as simplified radicals. So for example, if you have the square root of 18, well, we're going to want to simplify it by taking out any perfect squares. For example, we know that 9 is a perfect square, and 9 times 2 gives you 18. So since 9 is a perfect square, that's 3 times 3. So we take the square root of 9, which is 3, and multiply that with 2, giving us 3 square root 2. And that's a simplified square root. The quotient property is just a variation of the product property in that we are, we have a divided by b, the square root of a divided by b, which we can rewrite that as the square root of a divided by the square root of b separately. So for instance, here I have the square root of 2 divided by 25. I want to simplify this. 25 is a perfect square, so I start off by rewriting this as the square root of 2 over the square root of 25, and the square root of 25 is 5. Thus our simplified radical is the square root of 2 divided by the square root of 5. So for instance, if I were to let's look at the square root of 75. If I want to simplify the square root of 75, I ask myself, well, are there any perfect squares that go into 75? And there is. 25. So I could rewrite this as the square root of 25 times the square root of 3. Well, the square root of 25 is 5, so 5 square root 3 would be my simplified version of square root of 75. B here, we'll give a slightly different one. We have the square root of 7 times the square root of 35. Now, if we look at them individually, square root of 7 and the square root of 35, 35 doesn't have any perfect squares, and 7 is a prime number. But since we're multiplying them together, I could rewrite the square root of 35 as the square root of 7 times the square root of 7 times the square root of 5. So 35, 7 and 5, give us that. Well, the square root of 7 and the square root of 7, we have two of those. 7 times 7 is 49, and 49 is a perfect square. So really, because I have two 7's here, I could just rewrite this as 7 square root of 5, knowing that I could have multiplied these together. That's the square root of 49, and the square root of 49 is 7. So sometimes they present themselves like that. With the quotient property, we'll look at each of these individually. So, I have the square root of 100, so I can rewrite this as the square root of 100 over the square root of 169. And I ask myself, are there any perfect squares here? Well, these are both perfect squares. The square root of 100 is 10, and the square root of 169 is 13. So I got 10 over 13. In some cases, they're not both square roots. Let's take the case of the square root of 11 over 144. So I'll write these separately. The square root of 11 divided by the square root of 144. And, well, 11, there's no perfect square that goes into 11. So I'm just going to leave that as a square root of 11. But the square root of 144, well, there's a perfect square there, which is 12. I mean, the perfect square is 144, 12 times 12. So that's my simplified radical using our quotient property of square roots. So this comes into play, especially when we're dealing with conjugates and simplifying conjugates. What a conjugate is basically kind of how we can get rid of a square root. So for instance, if I have the square root of b, I can multiply the square root of b to get, well, b, and that gets rid of the square roots. In some cases, I'll get something like a plus the square root of b. Well, its conjugate, what I can multiply this binomial with, is a minus the square root of b, and that will get rid of our square root altogether. And vice versa. If I have a minus the square root of b and a plus the square root of b, that's going to get rid of our radical. The reason why we want to be able to get rid of radicals is we don't want to have radicals in our denominator. So we usually use this when we have a radical in the denominator of some sort of quotient. So, and this is called rationalizing the denominator. It makes our problem look nicer and cleaner and easier to work with. So for instance, if I were going to simplify these expressions, I have the square root of 2 over 15. So the first thing I want to do when simplifying this, and I'm going to use that quotient property, and I'm going to have the square root of 2 over the square root of 15. Well, I can't simplify either one of these in the sense that neither one of them has a perfect square that we can factor out. Instead, what I can do to simplify it is get rid of the square root of 15. We want to rationalize the denominator. So using that previous diagram or table showing us the conjugates, well, the conjugate of just the square root of 15 is going to be the square root of 15. So I'm going to multiply it by the square root of 15, the denominator. But I can't just do the denominator, because if I just multiply by the denominator, I'm doing 1 over the square root of 15, and I'm changing the value of the expression, and we never want to do that when simplifying. So I need to multiply it by 1. So I don't change the value. I'm going to multiply this by the square root of 15 divided by the square root of 15, which is just like multiplying it by 1. So it doesn't change the value, but now we can rewrite it in a simplified manner. So the square root of 2 times the square root of 15 gives us the square root of 30, and the square root of 15 times the square root of 15 is just 15. So I've rationalized the denominator. We no longer have a radical in the denominator, and this is a simplified expression. Sometimes we'll get expressions like this. So it's like 4 divided by 5 minus the square root of 2. And so I want to rationalize the denominator here, and I got to get rid of the square root of 2 in the denominator. So we multiply by its conjugate, which we saw earlier, would be a plus the square root of b, where a is 5 and b is the square root of 2. So I'm going to say 5 plus the square root of 2. Of course, we don't want to change the value of this. So we're going to make it 5 plus the square root of 2 over 5 plus the square root of 2. Now, keep in mind, when you have it written like this, there's like invisible parentheses around the numerator and denominator. They're implied. And so when I multiply the numerators together, then I need to know that, well, I'm actually going to be distributing the 4, multiplying the 4 to both terms. Because you'd actually, order of operations tells us we'd have to do the parentheses first. We'd have to add the 5 plus the square root of 2. But we don't want to have any decimals or any weird numbers. We're going to keep it clean. So I'll distribute the 4. So that's going to give me 20 plus, and then 4 times the square root of 2 is just that, 4 plus the square root of 2, or 4 square root of 2. And in the denominator, what I end up getting is, well, if you look at the form of this, this is like a minus b and a plus b. This is actually what we have here is form of a difference of squares. It looks just like it, and we could treat it as such. Remember, difference of squares, your first term is a perfect square, so 25, and then your second square is a perfect square. In other words, the square root of 2 times the square root of 2, which is just going to give us 2. And there's always a minus sign in between it. I can verify this, I know this for a fact, but I can verify it because we could multiply them together like a couple binomials. So, for instance, I'll illustrate this to you. I have the 5 minus the square root of 2 times 5 plus the square root of 2. So I distribute the 5 to both terms here. So I'd have 25. Let's see, and that's going to be plus 5 square root 2. And now I distribute this square root of 2, this negative square root of 2 to both terms. So that's going to leave me with minus 5 square root of 2. And then negative square root of 2 times positive square root of 2 is just going to give us a negative 2. And if we look at the middle terms here, they cancel out, leaving us with 25 minus 2. So it works just like a difference of squares. So I don't really need to do this, but it shows that, what's really going on here. So I'm left with 25 minus the square root of 2. Now we simplify that expression. Now the numerator, we can't add those together. I can't just say 20 plus the square root, 20 plus 4 square root 2. Similarly, I can't just say 20 plus, let's say the square root of 2 is x. Let's just say. You can't add 20 plus 4x and just say, oh, that's going to be 24x. Those are not like terms. So same thing applies here with addition and subtraction. These are not like terms, so we cannot add them together. So make sure you make note of that, because a very common mistake students make all the time. So write this down, make note of that, because I don't want you making that mistake. So I'm just going to keep it as is, 20 plus 4 square root of 2 divided by, and then 25 minus 2 is going to give us 23. And look, can I reduce anything? Does anything divide both the numerator and the denominator? No. So that's going to be my simplified expression. All right, so now let's bring in the quadratics now that we've done that. We're going to go ahead and solve for x, this quadratic, 2 and then x squared minus 15 equals 65. Notice that we don't have a bx term. We don't have just an x term. Solving quadratics by square roots, usually you only have just an x squared term. If you just have an x squared term, then you can use this method, and it will be the easiest and quickest method for solving as opposed to having to guess and check. So to do that this way, though, we want to isolate the x squared. We want to get the x squared on one side first. So let's see. We'll go ahead and we would add 15 to both sides, like so. So I'm left with 2x squared equals 80. And then we're going to divide both sides by 2. And x squared is equal to 40. Okay? So I'm looking at this, and I'm just left with the x squared, and that's what we want. We've isolated it, equals 40. Well, naturally, you've done this many times when dealing with the Pythagorean theorem. You're going to go ahead and take the square root to both sides. So I'm going to take the square root here and the square root here. But keep in mind that whatever this number is could be both positive or negative. So let me just do a side example here. Let's say, for instance, I have x squared equals 9, and I want to figure out what x is equal to. So I would take the square root of both sides here and here. And you would say, well, then x is equal to 3. But that's not entirely correct, because x could be negative 3 as well. Because we know that 3 times 3 gives us 9, as well as negative 3 times negative 3 gives us 9, a positive 9. So we have to account for both positives and negatives. So when we do that square root, we want to include what we say plus or minus. Okay, plus or minus. So I can write my answer into this little side example as x equals plus or minus the square root of 9, which means that x is equal to plus or minus 3. Okay? So likewise here, I'm going to make this plus or minus because of the x squared. The squared, hides the fact if it's positive or negative. So I'll be left with x equals plus or minus the square root of 40. Now we need to ask ourselves, can we simplify 40? Are there any perfect squares that go into 40? And there are. 4 is a perfect square. So I could simplify this as plus or minus, and then square root of 4 times square root of 10. And square root of 4 is 2. So x equals plus or minus 2 square root of 10. So we have two solutions here, positive 2 square root 10 and negative 2 square root 10. And I would box that in as my solution. So, make sure you simplify your radicals. They need to be presented in the simplest fashion possible. And don't forget that you're going to have both a positive and a negative option here. So let's look at an application. One of the most common applications you see when solving quadratics are height problems, usually when an object is dropped from a certain height. And that formula, and you're going to want to know this formula, so you're definitely going to want to write this down. H equals negative 16t squared plus h sub 0, where h is, whatever your ending height is, that's the, height it ends at, and h sub 0 is your initial height. So for instance, in this example, 200 is where we're going to drop our object at. And so that's going to be my initial height. So when setting this up, if I want to find a current height, then I would put in 200 as my initial height. And then the negative 16t squared, as we put in different values for t, time, and time is usually measured in seconds here. So like I could plug in, I could substitute in 1, and then my height would be 184. So 1 second, and my height would be 184. And then if I substitute 2 in for t, my height is going to be 136, and so forth and so on. And if my current height is, let's say, 0, that just means that we've hit the ground, okay, and we can't go any further unless we go negative, which would mean something else. So let's work out an example with this one. In our fourth example here, it says if you drop an object off the roof of an apartment building that is 240 feet tall, how long will it take the ball to hit the ground? So we'll start off by defining our variables, and I'm going to let t equal the time falling, and we will let h equal the ending height or final height, and h sub 0 is our initial height. So our formula is h equals negative 16 t squared plus h sub 0. So h sub our current height is going to be, or our ending height, our final height is going to be 0 because it's saying, when it hits the ground. And so our elevation, or our height, is going to be 0 at that point. We're looking to see how long it's going to take, so we're looking for time, and our initial height is going to be 240 feet in the air initially. So now it's just a matter of solving this. So I'm going to rewrite this. I'm going to subtract 240 from both sides, and I'm going to flip the equation around because I like my variables on the left. So I have negative 16t squared equals negative 240. Then we'll divide negative 16 into both sides here. So that's going to leave us with just t squared equals, and let's see, that's 240 divided by 16. So it's going to be 15 even. And now we just take the square root of both sides. Now, keeping in mind it could be plus or minus. So t is equal to plus or minus the square root of 15. Now we'll actually, with these word problems, we can actually come up with a decimal that will make more sense. But we have to think about, in the context of our problem, what makes more sense, a positive or a negative. And since we can't travel back in time, we're not going to use a negative value. Instead, we're going to use a positive value, talking about going forward in time. So I'll round this to the nearest hundredth. So since I'm rounding, it doesn't become equal, it becomes approximate. So that's our approximation symbol. And we'll say 3.87. So I would say, therefore, it takes about 3.87 seconds for the ball to hit the ground. And of course my pad is malfunctioning here, making it really hard to write. Anyway, that would be my solution I would box in. So anyway, that's solving quadratics by finding square roots.